So today I'm going to talk to you about, about one of the most exciting technical problems of the beginning of the 21st century, I have to say, is how do we build self-driving cars, autonomous vehicles? As you all know, it could change the society as we know it today, right? So imagine, of course, like if Uber or Google or all these companies were able to build L5, which is like, the final level of self-driving cars, fully autonomous cars. And you didn't have to buy a car, and the car would be an investment, and you would buy a car and you would rent it out, you would just run around the city, picking up passengers and driving them somewhere and so on. That's basically what Uber is betting on, right, to make money in the future, right? Because today they're not making any money and they are spending so much money on these teams busy trying to build those fully autonomous cars, same for Lyft, right? And so this is very exciting, and I'm going to talk a little bit about the problem statement, right? Why this is difficult, what is kind of the process of developing self-driving cars. Then I'm going to dive into our approach at solving that, right? From an engineering process perspective, our principles. Then I'm going to take a specific examples of how we apply those principles. And finally, I'm going to talk briefly about basically the platform we've built to sustain those efforts. First, let me talk a little bit about why self-driving cars, building an AI for self-driving cars is hard. I'm calling it an AI, right? It is an AI, artificial intelligence, supposed to replace humans, right, to drive cars. So I think in that case, it's okay. Is it okay? Right. Has anyone ever been in a Tesla, by the way, in the room? Yeah, on autopilot. Yeah, not that many people actually, right? It's not. Is it good?
Pretty good.
Yeah, it's pretty good, right? So in New York, it would be awful, right? It would be a disaster. And by the way, they just tell you that you shouldn't use it in New York and all that stuff, right? Exactly, right. So they just, but on highways, to do a lot of things like lane changes, all that stuff, it's really pretty good. So we already have an example of something that's working, a product out there that's working. And they're way ahead of the curve, right? And it is really hard, right? And that's why we only have, so far, one company doing it kind of okay, while the others are still building up their competencies in that space. So why is that hard? First, for all people developing deep neural networks on images and also other problems, whether it's NLP, even like tabular data for recommender systems and all that stuff, you know that we need to cover thousands of types of conditions and geolocations and so on. I mean, there are thousands of potential things that can happen, right, that need to be covered by this model. For self-driving cars, it's even more so. We have new, types of events happening all the time that need to be covered by the neural net, right? So driving on a French highway is completely different from driving on a US highway, which is completely different from driving in a city. And so, we have to, and on top of this, we have something like maybe 10 different neural nets, right, that are running in the cars, predicting different things. And that's, most of the self-driving cars makers are using similar techniques, right, where they have things like, hey, how do I know how much free space do I have, right? How do I estimate the distance, right? How do I detect obstacles? How do I do path perception and predict where I'm supposed to drive? So all these things are different neural networks. Even if they have the same body, there are still a few parameters that need to be trained independently. So it is difficult. This, on top of tons of geolocations and conditions, is pretty hard. This is technically, scientifically hard problem to solve. The engineering process is really hard too, because it mixes up tons of different stacks. So we go from a car, right? And so what happens is that when you drive that car, we are recording in real time all the sensors that come in, LiDAR, radar, all the cameras on the side, in the front, in the back, all that stuff at the same time. They all come with timestamps, right? They all come with errors sometimes, random bugs. All these timestamps are not aligned, right? So anyway, they get saved onto an SSD in the car. So every time you ride, you get terabytes of data, maybe. Then that data needs to be ingested. Just doing so is really a hard problem, right? The ingestion is let's plug this SSD onto a machine. That machine gets uploaded in the cloud, Well, anyway, there's tons of different steps of data processing that need to be run. Data needs to be indexed, so it's retrievable data, right? All of this is already a really hard problem that connects from the road to the cloud, I would say. Second step is like, once we have all that data, we need to be able to select it in an optimal way, right? Both for training, but also for evaluation. Training is important, of course, because we want to capture, we want to get better models and so on. But evaluation for self-driving cars is actually probably even more important. We need to be able to say, we can drive tens of millions of miles, that's the ultimate goal, right? Without any disengagement, right? Or without any problem. This is what humans are capable of doing, right? So we need to be able to evaluate on millions of miles. This is a lot of compute, right? Way more than whatever compute we need for training. So smart data selection, ability to sweep through petabytes of data and select the right data. Then of course labeling, right? We need to have a very efficient labeling infrastructure so we can take all that data and turn it into test, validation, and training sets. Well, then we do training, model search, and so on. And you see that's just a small part of this whole thing, right? It's not even like the biggest part in terms of like resources in that whole world. After this, once models have been trained, they need to be tested, right? This is what the industry calls or just re-sim testing. Re-simulation means running videos of already stuff that already happened, like existing videos, and running them through the system that is supposed to run in the car and see what happens, right? What are the logs? Is there some feature that's activated when it should not, right? How do we run that for like millions of hours and see if, for example, my object detection model missed a frame? I don't know, something like that, right? So this is what we call re-sim testing. It also includes simulations. So NVIDIA, for example, generates lots of simulated scenarios that we run through the actual inference software to see how the car behaves, right? Whether, and then we track metrics like, is it comfortable, not comfortable, all that stuff, right? So this is what this step is doing. And we need to deploy to the car. Optimize inference, we have like a latency budget that we need to respect, right? So we need to export our model from, say, TensorFlow or PyTorch to something that runs fast on NVIDIA GPUs. So we use, of course, we have NVIDIA and we have our own inference engine that's called TensorRT. This is what we use here. So yeah, this is the second reason why it's complex, like the whole process of building these, cars. Right, so the scale today. We have like 30 cars, not too much compared to Tesla, of course, but we don't plan on selling cars, right, at NVIDIA. We just want to solve that problem and then sell chips and software. We collect like maybe 1 petabyte of raw data monthly or something like that. We have 15 petabytes of proactive data. We have 1,500 labelers. Yeah, it's not a typo, it's like 1,500 people who label data. So we need tons of software to actually make them very efficient, right, to label data. We label 20 million objects a month. So it's like 1 million frames, but with 20 objects on average on each of them. We have 20 unique models, 50 labeling tasks, 500 petaflops of compute in our clusters, which is 4,000 GPUs. That's the good part, pretty easy for us to get GPUs. So. And then drive Pegasus in cluster. So that's an interesting one. Something we call constellation. We have the hardware that's running in the car is racked in our data centers, so we can actually run, as if it was in the car, right? So like everything happens as if we were in the car, so we can do proper testing. That's one thing that NVIDIA is pretty good at. It's like having this unified, hardware platform, basically. All right. So and we have tons of data, basically, tons of like object storage. Yes. All right. So now back going to our philosophy and our approach and how we want to do things. We think that creating the right data sets is the cornerstone of machine learning, at least for this problem, but it probably applies to many things. So if we start from a high level, here is how, you could describe the way software development happens from the perspective of an actual engineer, right? So we write code, turns into source code, that's the first iteration, that's great. Gets compiled, if you're lucky, right? Then you get an executable, you run this, and you see if you get the right results, right? Logs, this is what the logs STL compiler bit here is. Then of course, you want to iterate and make sure your code improves, right? It's faster, gets you the right results, you want to write unit tests, or like just add code, improve code, modify it, and then go back to the whole cycle. We see machine learning development as a similar, basically, cycle, right? Where we collect data instead of writing the initial code. We build a data set, so data set is our source code. Then instead of having a compiler, we have an ML algorithm that we can even treat as a kind of black box, right? If you think of how, for example, Google developed AutoML, right? They have the ability to just take like input, output, and define the model architecture for you, right? You don't really have to think about it anymore. So with the right software, we're able to define what the best model architecture is for a problem. So we can even treat this as a black box and generate a predictor. A predictor is like can be, just a binary that we ship and we say, okay, this is our model, predicts everything we need to know. Then we run that, and based on the results, right, whether it's actual metrics on the test set or any kind of like confidence estimate on our inference, we can modify, add, and improve our data set, and then recompile using our ML algorithms, get a new predictor, and so on and so forth. So the analogy is to say, well, source code, data is source code. Deep learning and machine learning algorithms are the compiler, and the predictor is the executor. That's kind of like the software 2.0 view of the world in a very dumbed down way. I'm not as smart as Andre Carpati, for those who know him, but basically that's we follow this approach. So that's very high level, but the way we see it is that data collection and ML algorithms are, like I've seen tremendous progress over the last 10 years. Even the systems to collect data and the systems to generate those the best ML algorithms, I've seen tremendous progress, right? However, what we think is lagging behind is the ability to introspect those predictors, right, to get the best information out of those, and the ability to like modify, improve the data sets in a meaningful way, like principled way. So yeah, based on this assumption, right, based on this assessment, we are we want to tackle those two problems and just, of course, build infrastructure to solve the data collection and ML algorithms, but really focus on the ones behind. We think this is going to be key to build the right data, which is our source code, right, and get to the best results. All right, so one example application of how we can build the right data sets is active learning. Who has heard of active learning in the room? Who knows about it? Yeah. All right, so quite a few people, but basically, we see it as a paradigm to iteratively develop machine learning data sets. Paradigm that can actually be automated. So I'm going to go through the case study of work we've done recently, and is showing very interesting early results. So, all right, why do we want to use active learning? So the first assumption is that, of course, like all data is not created equally. That means if you run for thousands of hours, you can find, for 1,000 hours, you're going to find 9.999 hours of like, highway roads like this with, cars, bright, all that stuff, right? And once in a while, you're going to have crazy friends like the one on the right, right? Where someone decides, I don't even know what they're doing, right? So just mining those frames, right, is very important because for our models, whatever is on the left is already completely solved, right, by our neural nets. I mean, maybe once in 100 million miles, we're going to find errors in those kinds of frames because of some very peculiar, particular lighting condition, right? But on the right, there's definitely something we need to be able to catch and know that we need to do something about it. We need to break. We need to do it right. So we need to export a deep learning symbol that says there is something on the road. It's a human. It's something, right? So yeah. So that's the first reason. Second reason is that data is expensive. As most of you probably already know, adding more data to a model improves it for sure, but like usually just in a very incremental way with diminishing returns. So the more we add data, after a while we need to add, I don't know, maybe 2x more data to get the same improvement, right? Or 10x more data. And sometimes we find internally that we actually plateau, right? So by just adding more data, the only thing we do is just solving the same range of events in a better way, where we're already performing almost perfectly. So it doesn't improve our model at all. We need to find new kind of like cluster of events, right, to improve this. So, and since we don't want to send like, millions of frames for labeling to get a very small improvement, we basically say, let's be smart about what we send to labeling. And of course, collecting data costs a lot, so like, running cars, ingesting data, saving it and other stuff. So this is another reason why we want to be pretty picky about the data we collect. Now, okay, let's look at object detection. So you see this is a typical frame where, we detect cars, maybe there's like a pedestrian on the right, I don't see any bicycles, but that's the idea. That's in San Francisco. Yeah, so if you look at this, our assumption is that the uncertainty coming from the model, so the object detection model in that case, is going to guide the way we select data, right? So if we have the ability to know which frames we're uncertain about, how are we going to, we're going to be able to, let's say, rank those frames by the top uncertainty and then select it, right? So in that case, I just showed two images with low uncertainty. So you don't see anything on those. These are regular images. That means the model is, is not uncertain at all about them, right? I'm going to define what uncertainty means later, but let's assume you have a score, right? A floating point value between 0 and 1, for example. However, here we have very interesting frames that were picked by our uncertainty score and that are in the top 100. So basically, in that case, we're looking at the pedestrian class. And what is the uncertainty about the pedestrian? So the heat map you see means that the model is uncertain about the specific area of the frame, right? So on the left, you see that we have a scooter, someone on a scooter, right? So it looks like a pedestrian, but at the same time, it's on the road. So we understand why the model could be confused, right? And it is actually confused. So this is something that we need to be labeled and be added to the data set, so we cover this use case as well. Same on the right, where we see kind of a person being drawn on a board, right? And so the model is confused about whether it's a pedestrian or not. So how do we have a few more examples like this for bicycles, for example, where we see bicycles at the back of a truck, bicycles at the top of a car, and the model is confused about those because it's not on the road, right? How do we compute uncertainty? We have a very simple way to do it that's scalable, requires quite a bit of compute, but doesn't require more time. So basically, we train the same model. In that case, you see it's a diagram of a unit, not what we use specifically, right, but just like a random diagram, so don't take it for granted that we use that, no? But basically, we can train, let's say, a pool of 10 models using different random seeds for initializing our parameters. And so what that means is that we train the model, up to, using early stepping, for example, up to a point, and then we take those 10 models, compute 10 different scores for each frame, and look at the disagreement between those scores, right? So we use mutual information in that case. That gives us a value of uncertainty, right? So you could think that, I think like the intuition behind that is that if the model doesn't have a good handle on certain events, right, then initializing parameters differently is gonna put those events, cluster those events in a completely different part of the space, right? If you train your model, so the model is kind of like gonna ignore it and then yield completely different results based on different instantiation of the random seed. So and this works out pretty well. Now in terms of testing whether this works or not, we found an interesting experimental setup that everybody could reproduce, right? Where basically we take a full training data set, and now our goal based on this full training data set is to see whether by selecting using those uncertainty scores and ranking inversely based on these scores, can we select the best frames, right? So what's difficult with that is to actually test that it works, you have to label frames. So instead of labeling frames, we take an existing data set that's already labeled, and we emulate the experiment. What we do is that we take like a random subset of it. So let's say we have 1 million frames, we're going to take 100,000 frames randomly. We're going to train 10 models on it, compute uncertainty scores. Once we have that, we compute uncertainty scores over the entire training set, including the one we already selected, right? So we can do replacement. And then we select, let's say, 200,000 frames that are either smartly selected or randomly selected. So you see how we are shaping up an A/B test where on one side we have completely random frames, we get 300,000 random frames. On the other side we have 100,000 random plus 200,000 smartly selected frames. And we can iterate on this, right? We can get results, train 10 other models to get uncertainty, and then select 200 more thousand frames, right? So this is the experimental setup to validate without having to label, right, and run an A/B test at scale, that our approach is reasonable. And the results are very interesting, of course. Now I'm just showing, cars in yellow and bicycles and pedestrians. And if you look at the performance after 300,000 frames, which is one iteration of random plus one iteration of smart selection, the dotted lines that are the smart selection algorithms are already way above the full lines, right? So what that means is that our metrics already completely outperform the just random selection. What's very interesting too is that we don't see it really well here, but it keeps performing even though we don't add unlabeled data. The reason for that is this algorithm is able to select the right amount of duplication for frames that are already in the dataset. So I guess like for all people who are in the room, you've probably already defined some kind of like duplication strategy for your models, right? So I don't know, you have like 2 classes or 10 classes. One is very balanced, so you're trying to add like maybe, oh, I'm going to duplicate those frames, right? Or I'm going to add a weight to my loss function or something like that. What this does is that it just computes the confidence cost even on frames that are already in your dataset. So then you can add more of those frames as well, right? So you could see it as a way to automatically duplicate frames in your dataset. All right, so basically conclusions on the prototype is that we are able to perform as well with like 35% of the data. However, smaller datasets are not always better because we need to train longer, so I don't know, not a huge benefit there. However, we see strong benefits in terms of performance compared to random selection. And finally, what I just talked about is that the ability to duplicate in a smart way is a candidate to eliminate manual heuristics, right? And that's something we discovered along the way where we're like, hey, well, wait a minute, why would we have data scientists work for months on some completely manual duplication selection, right, rather than use something automated like this. So we have a paper out that you can check, on archive that talks about this. All right, so now the next step for us is to scale this. To scale this, we need to implement this loop. First is doing ensemble training requires a lot of compute, right? If you have 10 models in your ensemble, 10 deep nets, it takes 2 days to train. It's like 10x more compute. It's not trivial, right? Then we need to sample unlabeled frames. That means be able to export, like for example, 10 billion frames that are unlabeled. Then we need to score them at scale. So score all those frames with the ensemble. So let's say if we have 10 models, 10 million frames, that would be 100 million scores, right, that we need to compute. So lots of compute power, more than for training, typically. So yeah, I mean, that's good. We have a lot of compute, right, but that's basically what we're doing. And then we want to do smart selection based on these scores, right? So for example, select the top 100,000, top 50,000, and then send them to labeling, which creates a new data set, right? Once we have this new data set, we train an ensemble up and close this loop. If we manage to automate all of this, we could even think that we could build data set automatically and just not do anything anymore, right? And just replace, just go on vacation, basically. So that's kind of what we're targeting, but requires a lot of work. Especially it requires a platform like that's not entirely there yet, but that we're building. So this is what we call MATLAB, and this is our internal production-grade machine learning infrastructure. So basically, this platform is all the software, all the tools, all the hardware as well, and all the level of software we use to implement this active learning loop, for example. That we need to implement this active learning. That we need to implement to do large-scale evaluation. We need to implement to do training as well, right? So all of this is implemented as part of this platform. So it's a huge effort. And so to go back to the process that we had before, where we ingest data, select smartly, do labeling, model training, re-simulation testing, and deployment. Basically, we drew kind of like functional blocks that we need to have in order to do a good job at this, right? So the first approach would be to ingest data, take your SSD, put it on your machine, and then train locally, right? So let's say you have a GPU machine. The first thing you would do is like, oh, okay, I'm going to put it there, I'm going to select data myself, label it, save it in a local file, on a local file system, right? And then train my model. And then, I would ship that model potentially deploy it to the car, and then run the car, right? But this doesn't scale, of course, right? So we need to be able to have like hundreds of data scientists working on those. We need to be able to store the results of a large-scale inference evaluation, right? We need to be able to have thousands of people working on labeling, all of this. So, of course, we need to build a platform that scales and tracks all the work that's been done. Otherwise, it's impossible to make proper progress. So we have multiple blocks, right? One is low-level hardware infrastructure, then all the data center backbone, which is like all the software we use on top of this hardware. And then we have all these functional blocks like how to manage data, how to manage workflows, and how to manage models. I'm not going to talk about labeling management because this is very, this is very like kind of on a different plane here, and it's a problem in itself. So I'm not going to go into that too much. But yeah, another way to see it, to see how we build a machine learning platform for these kind of problems, is by using a pyramid of needs, where we start with the most basic needs, where we need compute, right? Then once we have compute, we need a way to like orchestrate and schedule on a cluster of compute. So basically, this is where people are going to use Kubernetes, for example, or like Slurm, right? If they want to do HPC. The third layer is to have basically like tools that support support development. So if you have a team of 10 data scientists or 20 or 50, you probably don't want them to have their own frameworks, right? You don't want them to have their own library. You want them to collaborate and have a shared infrastructure, right? So this is the first step of like building a large-scale team to solve those problems. Then the next step is to have a much more principled way of scheduling tasks and dependencies between those tasks. Same about the data. How is the data indexed? How does the data depend on other data, right? What are the workflows between those kind of different pieces of data? About this, we need to have something like full reproducibility and traceability. In the case of self-driving cars, this is extremely important because let's say there is an accident with a Tesla, for example, and that, I don't know, there's an investigation going on, saying, okay, why was there an accident, that was on autopilot, who's responsible, is it the autopilot software? We need to know what exact data set was used to train what exact model at what time, right? And how it went into the car. This is extremely important. So this level of safety requires a level of software and tooling in the platform that's kind of like unparalleled in many areas. So, for example, we need to have the ability to guarantee that our data sets are immutable, right? Not have someone randomly modify those data sets on like a shared file system, for example. This is pretty tricky requirement, and that everything is automatically traced, right? Like the code. And finally, right, like the top of the pyramid is something like what I just described, like active learning, where we automate everything, we have the top technology, and we are making the best progress with the best applications on top of this platform. All right, so going very quickly on basically all the different tools that we have. I don't know if everyone is familiar with workflow systems. So kind of like the way to describe it is you can schedule a job on a cluster, saying, hey, I want to train my model. But you can also schedule workflows, which are like arbitrary graph of jobs. So I'm sure like a bunch of you are already familiar with this concept. But basically for us, it's extremely important because it tells us what depends on what, right? So if we generate a new model, we are able to then trace it back to all the inputs that we use to generate that model, right? The data set, I don't know, any kind of other arbitrary input that we want to have, right? And how those things fit into one another. So this is critical, and we could imagine having one workflow for, let's say, one neural network. And this workflow could include everything, starting from the data processing, and then doing all the training, fine-tuning, deployment, and then also finally doing all the testing at scale in the same workflow. And testing at scale means running thousands of jobs, parallel jobs on the actual inference hardware that we run in the car, but in the cloud. So all these things are extremely important for us. It's all traceable. Needs to be traceable. So yeah, these are kind of like the features we have. We need to be able to run it locally. We have a caching mechanism, traceability anyway. For those who are into this, we used to use Argo on top of Kubernetes, and we are now moving away from Argo because we were lacking flexibility. I'm not going to go into too many details, but basically Kubernetes doesn't scale really well to like thousands of jobs, right? And so we were hitting the limit. For example, one job we had for data processing we had to compress all of our data. It's like there was something like 17 petabytes of data, and we had to compress all of our data. So we decided to compress everything, almost everything, and it took all of the spot instances on US West 2 AWS data center, all of them 14,000 at some point, right? So it's huge, right? So like, I mean, this is a lot of data transfer and a lot of like compute. Try scaling 14,000 jobs on Kubernetes. It's probably going to break, right? Like the limit is 150,000 pods, I think. Anyway, so this is what Argo will do, right? Scaling jobs directly using the Kubernetes API. So we try to kind of like have a hybrid model where, you know, we generate kind of like workers, and those workers take work, but the scheduling is basically owned by us. Anyway, so that's the workflow management part. On the data side, so I mentioned, you know, the need for traceability and safety, and one very important point is the ability to have read-only immutable datasets and artifacts, right? And make sure that we know nobody was able to touch them. And even if someone could delete them, we know that they deleted them, right? So like, all of this is extremely important for us. Doesn't mean we don't want flexibility. So some of these bits of data need to be removable and we cannot store everything that the whole world produces for example, right? In terms of flexibility, we have a POSIX file abstraction of object storage, so everything uses object storage for scalability, horizontal like IO scalability. But we have a POSIX file abstraction on top of it. Maybe some of you are familiar with Fuse, S3 Fuse, for example. It's similar, but faster and read-only. We also have a read-write version, but you know we cannot separate the two because read-only has like way fewer constraints when we do deep learning training. Anyways, and finally we have a traceable query system. So every time you want a workflow with data, everything is traced. Everything is logged into a database, and you're able to then go to your notebook and say, hey, you know, basically tie a connection between any node in the compute graph that you had, and say, hey, tell me what the data set was, right? Like for this specific computation, what the graph was. So this is very helpful for us. And finally, model management. I think this is more typical, but this is about having all the blocks for deep learning development. So like mixed precision to accelerate training, optimize I/O, right? Pruning, exporting to our inference engine that's called TensorRT. What else? Like make sure that we can save the models along with their results, hyperparameters, so on and so forth, and then of course retrieving those results using like nice APIs. Very briefly, this is my last slide. Basically, this is our data center architecture. So this is our on-premise data center architecture. You see on the left we have a bunch of services on AWS with like not too much data transfer, but it's mostly for like services like the experiment service where we save our models, for example, right? So we have a pretty good connection to AWS, but we don't do anything crazy. However, all the heavy data transfer and I/O for deep learning training and deep learning inference happens on premise. And so this is kind of our rack design where we have something like 12 CPU nodes and 9 DGXs. DGX1 is like 8 volatile GPUs, 16 or 32 gigabytes of memory each, in a single server. I'm very happy to have that, It's really awesome, I mean, for people who like compute stuff, it's amazing. So we have those racks, they're really power hungry, of course, right? 35 kilowatts is a lot. And then on those CPU nodes, we run the storage that's hosted basically in the same racks, right? With a very efficient interconnection between the racks and between the nodes inside of the racks. And we use SwiftStack as our object storage software. And SwiftStack uses the same APIs as S3, so it's pretty easy for us to take this whole software stack basically and deploy it on AWS if we need to someday, right? Right now we don't, but everything is built to be open and like compliant with all the best APIs. So yeah, that's I like this slide because it's really scaling jobs on all these DGXs is pretty exciting. We can do multi-node training and that stuff. So yeah, that's pretty much it. Thank you very much.
Great, thanks. That's great talk. So we have a few minutes for the Q&A.
In one of your slides, you showed that there are certain things that your algorithm is not able to detect where you are doing the labeling. Is that labeling happening manually, like somebody sits and label it, or?
Yes. It's all images, all manual, and we have a lot of tooling to accelerate this. It's all manual. Yeah.
I assume there is a man driver drives around and collects the data, right? So if I drive around right now and collects the data, I'm going to collect only positive data. That means not a lot of folks are making accident if I walk around. So how do you collect negative data? Some of the people who breaks the law are innocuous. I mean, they're not trying to make an accident. They probably was driving in the middle of the lane. I mean, between the lanes or corner of a lane. So how do you come up with collect the data that is not necessarily negative, which comes between positive and negative? You know what I'm trying to say?
Yeah, I mean, when we collect the data, we don't really have an opinion about what we collect, right? First, it's like, whatever we collect. But then we need to build first the perception stack is based on deep neural nets parse processing that exposes high-level symbols. High-level symbols are things like, hey, here's the velocity, the depth, and the position of those vehicles. So this is still not opinionated, right? However, the next step is the control and panic that sits on top of the perception stack, and that's opinionated, right? So basically this is where you make decision about whether this is normal driving behavior or not, and how the car should drive itself to react to this, and what kind of signal it should send to the driver, for example. And this is a very tricky problem, basically, right? To be able to understand what's normal and what's not, right? So, I don't know if that really answers your question, but basically we delegate the responsibility of this problem to the control and panic stack, which, luckily for me, I'm not in charge of. So, yeah.
Can you talk a little bit about the model management in your pipeline, like versioning, deployment?
So in terms, okay. So let me see. What do you want to know exactly?
Like how you manage model, where's the model sit? I mean, how you deploy which model, the versioning.
Oh yeah, right. Okay. So I mean, we have a way to, well, of course, we have raw storage, right, to store whatever we want, and then on top of it, talking to the storage, we have a bunch of services. One of them is called the experiment service, and the experiment service lets us save models, save KPIs attached to those models, give experiment names to those models, and so on. So basically, we have this kind of database of models and KPIs, and associated to the workflow it was run from, and all that stuff, right? So that's step number one. Then in order to select the models that actually go into the car, there is a huge step of testing, right? And how to verify whether the metrics that we care about are good enough. So these metrics can also be set to the same experiment service. It could be something like MAD, which is mean autonomous distance. How long do we drive without any disengagement from the car, for example, right? We can have, there are a ton of other things we can track. Once we have all of this, then we decide whether we take that model and put it in production instead of the one we already have, right? Based on a series of metrics. And then once we do that, we export our model into the format it is in. So something like HDF5 for Keras, or Protobuf for TensorFlow, or whatever for PyTorch. And we turn this into an inference graph. That's using TensorRT, which is our own inference engine, that's optimized for our hardware, right? And then of course we have software to do this, and we have then the storage that also lets us save this optimized inference engine model. Does that answer your question? Okay.
Great. I think this topic probably need another tech talk sessions this afternoon. Okay, I want to give some questions from this side.
Hey, thank you. Great presentation.
Thank you.
So, looking at the whole infrastructure that you have built, do you see NVIDIA taking this out and basically opening it up for the world to basically use that infrastructure, rent it? That's just like AWS today. Do you see that happening at some point or not?
So it depends what part you're talking about. Are you talking about the cloud ready part?
Yes, the cloud ready part, where you could just access the APIs and
Yeah, I can't really answer that right now, but I think at least one thing is for sure is the strategy of NVIDIA is to build an open platform. Our goal is not to sell cars, right? So as a result, what we want is people to use our hardware and make our hardware more valuable by building the software that runs on top of it, right? So whatever gets us closer to that goal, is something that makes sense. But one example is that we do provide our inference software that's called DriveWorks to external customers, right? In the form of a binary with APIs, they can add their own modules on top of it. And so we already do that, right? So yeah, like it's regarding the cloud itself, yeah, that's a discussion. So.
Thank you.
Let's get to the last question.
It seems like you're collecting an awful lot of data, and personally, when I learned how to drive, I didn't need all this boxes coming down from the West Coast to learn how to drive. I'm just curious what the sort of how well all of the model actually translates to real world results. You said you have 5 cars that actually drive or something like.
Totally.
Yeah, on highways. How well is your service quality against a Tesla? Because I don't think Tesla has such an exhaustive function.
Yeah, that's a very good question. But by the way, I mean, you didn't know how to drive, but you were a baby for a very long time, right? And then, you just went around the highways and did stuff. So, yeah. Oh yeah, it's an embedded. You don't even know what it looks like, right? But yeah. So we don't have as much data as Tesla, for example. We don't have the same fleet. The way Tesla is doing it, and I think they presented that like a few weeks ago, a couple of months ago, is that they have software in the car that selects the most important segments of video that they wanna, that they think is important, and then they upload it to their cloud over the Wi-Fi every night when you come back to your garage, right? I mean, that's awesome. I would love to have that, right? They have like hundreds of thousands of cars and they can do that. That's a good problem to have. NVIDIA doesn't have that. However, we are completely in control of where our fleet can go, right? So we know we can have campaigns of collecting data where we want to collect data, right? Doesn't let us select things that are very rare, for example, but at least it can. If we need data, more data at night, more data in cities or whatever, then we can ask for it, right? So it's a different. We try to do it that way. The other thing is that we are partnering with, we recently signed a deal with Volvo Trucks, for example, and so Volvo Trucks is going to collect a lot of data as well, right? So we can think that, which is more like similar to what mobile is doing, where we collect data from partners, right, and then we can also have access to more of the data. So yeah, it's more hybrid, and we don't have the same strategy in that respect, but yeah, that's how we do it.
Great, thanks so much, great presentation.
Thank you.